Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our last speaker, really requires no introduction, but how many of you guys know the story of Apple back in the 70s? Not that many hands, okay. So there was this thing where, Steve Jobs and everyone, they were looking around for stuff, and at some point they came about the Xerox PARC Lab. And this is, I think, almost one of the quotes from Steve who said that those guys had invented the future. Back in the 70s, they had GUIs and WYSIWYG and the best operating systems and programming languages and mouse and networking, email, everything was invented back in the 70s, and he was completely taken by it, right? And he made that into something that every one of us now has in our hands. Our laptops, our phones, everything sort of was the genesis. Now, one of the people who founded Xerox PARC is right here with us, Dr. Butler Lamson. And he has had such a phenomenal impact on computer science, every aspect of it, that is just mind-blowing. Like if I started talking about it, I'd need a separate slot to just introduce all the things that he has had an impact on. But I know you guys want to hear more from him, so let me invite Dr. Lamson on the stage, and let's give him a standing ovation.
Thank you, everyone. Now, we didn't quite invent everything. We didn't invent spreadsheets. And that's actually a good lesson in that, because I think the reason we didn't invent spreadsheets was that we didn't have any use for them, since we didn't do accounting. And nowadays, of course, spreadsheets are used for lots of other things. But in those days, they were mainly used for accounting. So 30 years ago, I wrote a paper entitled Hints for Computer Systems. Wonder why it's running off the edge. That's distressing. You're supposed to do something that can be done. Maybe it's okay here. Oh, it's okay here. It's just these screens that don't work quite right. If you haven't read this paper, you should read it, even though it is 30 years old. I reread it myself every 3 or 4 years after I'd written it, and for about 15 years, I didn't really feel much of a need to update it. But starting about 10 years ago, I started to feel that the world had changed enough, and I had learned enough new things, that it was really a good idea to write a new version. So I've been working on that for the last couple of years. I have to say, not very successfully. My problem now is that I know too much. 30 years ago, I knew just about the right amount to fill a paper of hints. So here I'm just going to give you a sketch of all the things that I think I have to say today. Please bear in mind, these are hints. They're not guaranteed to be consistent or reliable or always applicable. If you don't like them, just ignore the ones you don't like and press on. You're not allowed to nitpick them. So I've summarized most of what I have to say in the way of hints under 2 headings. One of them has to do with what you want the system that you're building to accomplish, and the other one has to do with how it goes about accomplishing it. So there's a nice little slogan, steady by aid. We'll see that I've classified the goals under 6 headings: simple, timely, efficient, adaptable, dependable. Those are all phrases, well, maybe timely you haven't heard in your courses, but you've probably heard all those other words in your courses. And the last one, which was suggested to me by Larry Rudolph a few years ago, is yummy. I'm not going to have a lot to say about what it takes to make systems yummy, but if you study what Apple does, you can have a good idea of at least one way to go about it. And it's important to bear in mind that for many of the kinds of systems that you want to build and deploy, yumminess is extremely important. If it doesn't appeal to people in some fairly strong way, they're not going to accept it and adopt it. And under how, I've organized the thoughts under these 3 headings: approximate, incremental, and divide and conquer. And we'll see how all this goes as we go along. So here are the goals again. You might want your system to be simple. It might be very important for it to be timely, that is, get to market quickly. Efficiency is often important. Adaptability is frequently important. Some kinds of systems, for instance, air systems that control airplanes, have to be dependable. And I already talked about yumminess. And I marked in red the half of the goals that I think are much more important today than they were 30 years ago when I wrote the original paper. Of course, all these are all good things. Ideally, the system that we build would have lots of all of these things. In fact, of course, you can't have everything that's good. Engineering is a matter of making trade-offs. So one of the values, I think, of having a list like this in front of you is you have to ask yourself very seriously, which of these things is the most important to me? And which are the ones where I can afford to not do so well? Because you won't be able to do extremely well with all of them. And under techniques, I have these three major headings: approximate, do things incrementally, and divide and conquer. And we'll see a lot of detail on all of those in the second half of the talk. Before I plunge into details on each of these things, I just want to say a couple of things that have more broad applicability. Often it's very helpful to think about the alternatives that you have in designing a system in terms of oppositions. And I actually have a list of 10 or 15 oppositions, and I've just put a couple of them on this slide. One that I think is very important is the distinction between approximate and precise software. A precise software is software that has a spec, whether or not the spec is written down. And if the software doesn't satisfy the spec pretty well, the customer is going to be very unhappy. Now, the slogan for that is get it right. So avionics software, banking software, productivity software like Microsoft Office. These are things where it's very important for the system to be right, and if it's not, the customers are really unhappy. Not that it's going to be absolutely perfect, but it has to be pretty good. Approximate software, on the other hand, typically doesn't have a spec. There is no spec for Google search, for example. One could attempt to formulate one, but first of all, it wouldn't really be very good, and secondly, it has absolutely nothing to do with the success or failure of Google. Similarly, if you are a customer of the Amazon website, you may have noticed that a lot of the information that they give you on the web pages that pop up as you navigate the site, a lot of the information on occasion is missing or even wrong. They made a deliberate decision that, although it's very important to have the page that has the place your order button on it, have the correct information. The rest of the pages that are trying to suck you into buying things, timeliness, agility, visual appeal, and things like that are much more important than having every detail right. So the slogans for approximate software are get it soon and make it cool. And sort of old-fashioned computer scientists don't like this story that I just told you at all. They take the view that precise software is the only kind of software that's any good. That is definitely not what I'm telling you. Precise software is neither better or worse than approximate software, but it's different. And if you don't understand which kind you're building, you're going to waste a lot of time and energy making it more precise than it needs to be, and then it won't be ready soon enough, or it won't be able to change quickly enough. On the other hand, if you are building approximate software and it should have been precise, your customers are going to be extremely unhappy. The other opposition that I've put here is one that I like really because I found 7 words that start with F that are a good way to summarize the steady slogan. Another overarching point that I wanted to make has to do with coordinate systems and notation. In many cases, success in understanding what your system is doing and in designing it well is made much easier if you adopt the right coordinate system. If you remember your study of elementary physics, if you're doing dynamics problems, often it's much easier to solve the problem in the center of mass coordinate system. Similarly, if you're working with matrices, it's often very much easier to understand what's going on if you switch to a coordinate system in which the eigenvectors of the matrix are the coordinate axes. I'll just give a couple of examples of this. There are a number of them that I think are pretty convincing. The one that I like the most is the difference between viewing state as being and viewing state as becoming. We're accustomed to thinking of state as being. That is, there's a whole bunch of variables, memory locations, or variables in a programming language or whatever, and they all have values. And you can find out the things that are easy to do are to find out the value of a variable or to change the value of a variable. That's state as being. State as becoming is about how you got there. What is the sequence of operations that got you from some previous state to this one? And if you represent the state that way, it's not so easy to perhaps to find out what the current value of the variable x is, but it's much easier to do things like recovering old versions of the state, because you can do that by just replaying the sequence of actions up to the point of where you wanted the old version. It's much easier to do error recovery that way. And there are a number of other things, basically having all in one way or another having to do with your desire to deal with more than one version of the system at a time, which are much easier to do if you take the becoming point of view. A second example of different coordinate systems is thinking of a function as code versus thinking of a function as a table of arguments and associated values, versus thinking of a function as an overlay. That is, you have some partial function, you try it first, and if it turns out to be undefined, then you try some other function. So an example of an overlay, that's probably the one that's the least familiar to you, but an example of an overlay is a memory system with a cache, where if you're the processor and you want the value of location 10, first you look in the cache to see if location 10 is there. There's a table of locations and values in the cache, but it's not complete. If you don't find it in the cache, then you go to the main memory. So that was cache overlaid on main memory. And thinking of things in these terms often makes it much easier for you to see what's really going on in your system and what the design alternatives are. A related point, which I'm not going to delve into, is the importance of using a good notation, having vocabulary that's well matched to your problem space, and syntax that makes it easy to express the things that are important in your system. And this is why domain-specific languages are so successful. And the final overarching thing I want to say is, and this is the most unpopular one, is you should write a spec for your system. Even if it's an approximate system, you should write some sort of a spec. At the very least, what you should do is write down the abstract state of your system. So you may not be familiar with the idea of abstract state, but I'll give you just one example. The abstract state of a file system is a map from path names, that's the path name of the file, to byte arrays, that's the contents of the file. And there are many, many different ways to implement this abstraction, but that's the abstract state. Then if you want to go far, and typically I've found that just writing down the abstract state gives you half the value that you're going to get from writing a spec at all. It's actually surprisingly hard work to write down the abstract state, because you have to shake your mind loose from all the implementation details that are probably filling it, and understand what it is that is really going on in your system from the point of view of its users. Then if you want to go farther, you should write down what the interface actions, what the APIs are that you can use to operate on the state. And finally, if you want to go closer to establishing confidence that your implementation actually does what the spec says it's supposed to do, you should write down the abstraction function, which gets you from the concrete state that the code uses to the abstract state that you did on the first line. And then if you actually want to do a proof, there's a general purpose way of doing that, which I've sketched out. If you want to pursue these matters in more detail, you can look at the course notes for the course I taught at MIT for a number of years on this subject, which you can find on the web. Enough about that. Okay, so now I wanted to talk about the goals, and after we've done that, we'll talk some about the methods. So the most important goal typically is keep your system simple. KISS stands for Keep It Simple, Stupid. Why is it so important for the system to be simple? It's for one reason. We're not that smart, and we can't do that much. And if the system is not simple, you won't be able to understand it, and it will spiral out of control. Making things simple is hard, and often it's not rewarded. If you work hard to make something simple and you tell people about it, frequently their response will be, oh, that's obvious. But I assure you, if you had asked them to explain it before you did, they wouldn't be able to tell you this obvious thing at all. Often, simplicity is not rewarded. A question that I've pondered on many occasions, and I think I know the answer to, is why was the web not invented by a computer scientist? Why was it invented by a sort of ersatz physicist? And I think the answer is it's too simple. If someone had written a paper for an operating systems conference or an information retrieval conference or anything like that describing Tim Berners-Lee's design for the web, it would have just been laughed out of the room. Every time you click on a link, we're going to make a new TCP connection? Come on, that's ridiculous. But actually, I think he made just about every design decision precisely correctly, because every design decision was made in the interest of simplicity. On the other hand, we did succeed in inventing the internet, although it was a slow, painful 10-year process. How can you tell whether your system is simple enough? Well, the basic criterion for simplicity derives from the first line on the slide. It's simple enough if you can actually understand it. But the problem with that rule is what's going to happen when the system evolves? As it evolves, it's going to get more complicated, and then you won't be able to understand it anymore. And the only thing that can save you in that situation is abstraction and interfaces. And we'll talk more about that later. Timely. The slogan here is keep it real. Good enough is good enough. It doesn't have to be perfect. In fact, I firmly believe that the main reason the web is successful is that it doesn't have to work. And very frequently it doesn't work. You push on the link and the wrong thing happens, and you have to go back and push on it again. It's okay. People have a lot of tolerance for this sort of thing, and the web takes an enormous amount of advantage of the fact that the basic model says that it's a person at the other end who can deal with a lot of things that go wrong. Many errors, even aside from the web, many errors in computer systems are not fatal. You can retry things, you can undo the thing that was done by mistake, or the errors just aren't that important, as in the story I was telling you about the Amazon retail web pages. The other important aspect of timeliness, get it out there quickly, is that you find out what it is that customers really value, as opposed to what you imagine they value. And if you're Steve Jobs, you just know what it is that customers are going to value, and then you don't need to do this. But if you're any ordinary person, most likely your idea about what the customers really want will be pretty different from what it is they actually want. And the only way you can convincingly find out what they actually want is to give them something and see what it is that they don't like about it. I used to be very unhappy with Microsoft's habit of putting out half-baked software as version 1, but based on the argument I just gave you, I'm much less unhappy with it now than I was 10 or 15 years ago. Okay, the E in steady is for efficiency. The slogan here is reduce waste. And the important thing to bear in mind is that it only needs to be efficient enough. It does not have to be optimal. Typically, there are a few situations in computing where the search for optimality is worthwhile because there's so much money at stake. But most of the time, it's much more important to avoid disaster than it is to make your system optimal. The other aspect of efficiency is you need to understand what it is that's important for you. Many people hear the word efficient and they think, oh, that means it should execute in the shortest amount of time. But that is often not the thing that's important. Perhaps it's the people cost to administer the system that's most important. In that case, you need to standardize things and automate most of the administrative tasks. Perhaps it's the hardware cost for providing a stable service. In that case, it may be very important to write tight code. Perhaps it's the non-recurring engineering cost and the ability to get to market quickly. In that case, you should use big components. Even if they're wasteful, you should burn hardware, and you should settle for something that's good enough. Adaptable. This is one of the things that was not so important 30 years ago. 30 years ago, typically, we built systems to run on a given set of hardware. They had a pretty well-defined task to perform. You constructed them to perform that task. You had a pretty good idea of what the user community was, and things more or less stayed put. Nowadays, there are many ways in which systems need to be able to evolve if they're successful. Of course, if the system fails, it doesn't matter. So you want to plan for success. Systems need to adapt to size. Successful systems live for a long time, machines get faster, load increases, features get added. The canonical example is the web, which grew from 100 or so users to the 10 to the 9th users that we have today. So that's 7 orders of magnitude, which is a big amount of scaling. Systems need to be able to adapt to change and to be updated incrementally. So big things typically change only a little bit at a time. And there's technology in databases and web indexes for complex and dynamic arrays for routing on the internet. Many, many examples of techniques that allow you to make changes a little bit at a time. And finally, systems need to adapt to failure. Many kinds of systems need to be fault tolerant because crashes, errors, and bugs are just unavoidable. You have to plan for them and be able to adapt to them as opposed to trying to stamp them out. Dependability. Dependability is not having to say, I'm sorry. And it comes in 3 parts. Many of you have probably already seen this. You want your system to be reliable. That is, you want it to give the right answer. You want it to be available, which means you want it to give that answer promptly. And you want it to be secure, which means that it does those things in spite of bad guys that are trying to mess it up. The big issue with dependability is to make a judgment about how much dependability you really need. That depends very much on the customer. And often these decisions are not made sensibly. For example, about 5 years ago, the British rail system had a couple of fatal accidents. And as a result of that, there was a big panic. And they spent a huge amount of money on various sorts of safety-related upgrades. And it was calculated that the cost per life saved of all these upgrades was about $1 billion per life, which means it's not a good way to spend the money because you could save a lot more lives for that $1 billion than the one life that you spend by saving it on improved railroad safety. Another good example is the phone system. The US phone system today is quite a bit less reliable than it was in 1980, quite a bit less dependable than it was in 1980. But on the other hand, it does a lot of wonderful things like allowing you to carry around your phone connectivity in your pocket that it was unable to do in 1980. Okay, that was the summary of techniques. I didn't talk about yumminess because I don't really understand much about yumminess. It's not what I do. But it is important to bear in mind and to think carefully about whether an important part of your system is that your customers will really bond to it. Okay, the rest of the talk I want to spend discussing techniques for achieving these goals. And I've classified the ones I'm going to talk about under 3 major headings, which are summed up as aid. So there's approximate, there's do things incrementally, and most important, there's divide and conquer. I looked very hard for an acronym that would start with divide and with D, since it's the most important, but I couldn't find one. I did find aid. So divide and conquer has a lot of aspects, and here's the most important one. You want to divide things up by difference, which means you want to divide your system up into abstractions with clean interfaces. Why is that important? Because it limits the amount of complexity that any individual needs to deal with. The overall system architect has to understand all the abstractions and how they fit together using the interfaces that are being defined. But the overall system architect doesn't need to be able to understand the details of what's going on inside each one of those abstractions. In fact, the whole point of the abstraction game is that different people can work on separate abstractions independently. And the only thing they have to worry about is satisfying the specification, satisfying the interface specification. So we have all kinds of examples of how this has paid off big time in computing. TCP/IP is perhaps the most outstanding example, where because that's a very simple, very clean, very stable interface, it's been possible to do an enormous number of different kinds of things on top of it. The web, email, FTP, video conferencing, all kinds of different things. And it's also been possible to do all kinds of different things down below that interface. Many different kinds of networks, physical and logical networks that can sit underneath the TCP/IP interface. Another illustration that hasn't been as spectacularly successful as TCP/IP, but it's been pretty successful, is file systems, where there's a so-called virtual file system interface, on top of which you can build all kinds of applications that operate on files. And then down below that interface, you can have all kinds of different implementations on many different kinds of physical devices over networks, copy on write file systems, lots and lots of different things. A special form of abstraction is the thing that people call platforms or layers. And here the idea is you don't just divide the whole system up neatly into pieces, but you structure it into big collections of pieces that have some amount of coherence to them. So for example, the operating system provides a platform. It has a lot of different pieces of functionality. There are a lot of different modules, a lot of different abstractions in an operating system with a lot of different interfaces. But the operating system as a whole is something where you can say, this is Windows 8.1, and people can program to that, and Microsoft can ship it as a single entity. And that makes the evolution of a big thing like that much easier and more, in fact, more. Without that, it wouldn't be practical at all. If you shipped the individual components of the operating system separately, no one would be able to keep track of all the resulting complexity. The browser is another example of a platform. The x86 processor is another example. The internet is another example. Sometimes the role of a platform is a little bit more abstract. You might, for example, say that a platform provides transactions that allow you to do complicated things atomically. Or a platform might provide garbage collection, which takes care of most of the complexity of memory management. And that can drastically simplify the life of the clients of the platform. I think we'll skip over the synthesis thing, even though it's dear to my heart. So that was dividing by difference, abstraction. Here are other kinds of divide and conquer that can pay off big time. Recursion is important. Here you divide by structures. You try to take advantage of the fact that you can view the part essentially in the same way that you view the whole. Many of you have probably encountered quicksort. An interesting example of an algorithm which is essentially state-of-the-art for single machine sorting, but it's also 45 years old and can be taught in an elementary algorithms course. And the basic idea of quicksort is to recursively subdivide the entire pile of stuff that you have to sort into halves and keep doing that until you're down to something that's so small that you can sort it some other way efficiently. Distributed hash tables are another example of recursion, where you take a single hash table that can be implemented on one machine and subdivide it recursively into a whole bunch of sort of sub-hash tables that you spread out according to some hash function around the ring or tree structure of the distributed hash table. Path names that you're familiar with, certainly from file systems and perhaps from IPv6, is another example of recursive structure, where you know that a single file system directory can look like a whole file system by itself, and that each one of the subdirectories of that guy can also look like a whole file system by itself, and so on all the way down. Replication is dividing for redundancy. And you can do that either in time or in space. Doing it in time is usually called retry. The canonical example of that is the TCP protocol, which is an example of the idea of an end-to-end check, where you do some more or less complicated thing, you have some way of checking whether it worked, and if it didn't work, you can go back and retry the whole thing for reliability. The other way to do reliability, the other way to deploy redundancy in order to get a fault-tolerant system is to do it in space, make several different copies of the thing that you're trying to accomplish, and find some scheme that guarantees you that each of those individual copies, well, to first approximation, each of those individual copies either is going to stop working entirely, or it's going to do the same thing as all the other copies. Finally, divide and conquer. If you want to divide for performance, the name for that is concurrency. And that's becoming increasingly important in the modern world, since we don't get the individual processors to be faster and faster, but we do get more and more of them. So if we want our entire system to run faster, we have to figure out a way to make it run concurrently on all the different processors that we get. So, you know, today in a high-end, well, even in a low-end system, you get 8 cores. And then if you really want to do a lot of computing, you get yourself a cluster with 1,000 machines in it, each one of which has 8 cores, or maybe even more. So you need to have, in many cases, you need to have concurrency that works at the level of hundreds or thousands or tens of thousands of items. My slogan for concurrency is a simple one. Your choices for a concurrent system are stripe, stream, or struggle. Striping is something that works when you have a lot of pieces of the computation that are very similar and completely independent of each other. And then you dole them out, one to each processing unit. Streaming is something that Jeanette had referred to earlier, but under the name of pipelining, where you string things together in such a way that each element feeds the next one. And if you can't figure out how to make your concurrent system either striped or streaming, then you're going to have to struggle. It's going to be hard work. So I highly recommend trying to make it so that it's either striped or streamed. BitTorrent is a good example of striping. MapReduce is a good example of both striping and streaming, if you're familiar with those systems. Okay, that was a divide and conquer. That was the most important thing. The other two are also pretty important, though. Here's incremental. So the idea here is to do things a bit at a time and somehow put all those bits together to achieve the total of what you want to accomplish. And the most important idea for incrementality is composition. If you have 2 instances of something and you can somehow put them together to make a bigger thing, that allows you to work a little bit at a time. So for example, composing relations, that usually goes under the name of join. And if you're familiar with relational database systems at all, you'll know that that's pretty critical. Similarly, composing processes is done with fork, inter-process communication, and join. The most important example of composing in most systems goes by the name of indirection. And I'm very fond of David Wheeler's saying that any problem in computing can be solved with another level of indirection. So the basic idea of indirection is that you have some control over the mapping from names to values. One example of this, which is very common, is virtualization. Virtual machines are the most familiar example of this, where the original idea was you've got a piece of hardware, you have a memory and some instructions, and the instructions operate directly on the memory. What virtualization does is it puts in a layer in between there so that you can intervene in the execution of every single instruction when that's necessary, and you can intervene on every single memory access if that's necessary. And then there's a bunch of clever implementation tricks that make it so that although it's possible to intervene on every single instruction and every single memory reference, almost all the time it's not necessary. So almost all the time you can run at full speed. But virtual machines have pretty much revolutionized the practice of deploying applications on large numbers of servers. Another example of virtualization is so-called network address translation, which is the trick that's used to make it so that even though we only have 10 to the 9th IP addresses, 4 times 10 to the 9th IP addresses, nonetheless, we can handle a lot more than 4 times 10 to the 9th internet-connected devices. And the way that's done is by interposing on the, virtualizing the IP addresses, essentially. A third example is USB, now the standard interconnect for plugging relatively low bandwidth I/O devices into computers. And if you look closely at USB and you ask, for example, how does the USB actually connect a keyboard to the computer, the answer is there's a hoary old 30-year-old standard that was used on the IBM PC in 1981 for connecting a keyboard to a computer. And all USB does is to wrap that standard in the USB protocol, thus virtualizing it, transmit the bits of the old PS2 keyboard standard over the wire using USB, and then unwrap it at the other end. That's another example of indirection. In the network, you can have an IP address, or you can have something that's less direct, which is a DNS name, or you can have something that's even less direct than that, which is some service. Symbolic links, virtual methods in object-oriented programming, copy-on-write file systems. You may not know about all these things, but these are all examples of the application of indirection. And again, the basic idea always is somehow you're going to interpose on the direct name to value mapping to make it, give yourself more flexibility. Other aspects of incremental besides composition, there's iteration. You can iterate the design process. You can iterate actions in a loop or a recursion. You can iterate components. The most striking example of this that I've called out here is the idea of redo, where you take the sequence of actions that you've done and you put them into you record the sequence of actions in a log so that if something goes wrong or you need to do it, replicate the same computation in another place, you can just replay those actions. A third example of incrementality is the ability to extend things. So you start out with a basic design, for example, for basic HTML, but it's been an essential part of the strength of HTML from the beginning that they have a rule that says you can have an arbitrary number of tags on HTML nodes, and if someone who's reading a piece of HTML doesn't understand a tag, they can just ignore it. And the result of that may be that you don't get the full functionality that you would have gotten if the tag had been understood, but you get some functionality, and it doesn't break the receiver. Ethernet is another example of extension. Ethernet started out in 1980 with a protocol that ran over 10 megabit shared media, and today it runs over 40 gigabit dedicated media, still using exactly the same basic protocol, packet formats and things like that, so that all these different physical media can interoperate because they gave careful thought to how you were going to make it extensible. Okay, so we did divide and conquer, we did incremental, now we're going to do approximate. So the most important idea for approximation, of course, is one that I've already touched on in the context of goals, which is settle for something that's good enough. Don't try to make it perfect. So for the web and for search engines, you're sort of stuck with this idea because there's not, the idea of making it perfect is not even meaningful. IP packets are another example of good enough, where the rule is, in the networking world, it's called best efforts. And the rule is, I put a packet into the IP network, and the network is going to try to get it delivered to the other end. But if things get too tough, you're going to drop the packet on the floor, and the client is going to have to be able to deal with that by some higher level mechanism, usually by TCP. You might not know that in the original ARPANET, they didn't have best efforts. The original ARPANET design said that if the network accepted a packet, it would bust its gut trying to get the packet to the other end. And in the course of about 5 years, they discovered that this was a really bad idea. And they had to have an extremely painful switchover, sort of a D-Day, at which they abandoned this guarantee in favor of best efforts. Other examples of doing things approximately, the philosophy of loose coupling, for which my slogan is springy, flaky parts. You want your parts to, you want to recognize that the parts are going to be flaky. They're not going to be perfect, but you want them to be springy so that they can absorb the jars caused by the flakiness and still deliver an acceptable amount of service. So email and the Fedwire for transferring money around between US banks are examples of that. Approximating in terms of resources that you need, here the idea is, if at all possible, use brute force. Brute force is simple. Often it's a lot cheaper than spending the brain power to figure out how to do things more economically. Over-provision your hardware, broadcast your packets. If it looks as though something's going wrong, crash quickly and reboot quickly, and that's much better than trying to fix things up. Relaxation is often a good strategy. Take small steps that are going to converge to the desired result. So the exponential backoff that Ethernet and TCP use, the idea of eventual consistency for updates, where you trade perfect consistency of the store for the ability to operate even when some parts of it are not working or are partitioned off. The idea that you should do daily builds of the system that you're trying to build. All those things are examples of applying the idea of relaxation. So to sum up, I've given you some hints and a few principles. The difference is the hints are just suggestions. The principles are sort of demands. If I were your boss, I would be mad at you if you didn't follow the principles. And the slogan is steady by aid. Make things simple, timely, efficient, adaptable, dependable, and yummy. And you have a whole raft of techniques for doing that, about three quarters of which fit under the rubric of approximate, incremental, and divide and conquer. Well, that was a lot of stuff to hear. Most of it probably went in one ear and out the other. If you just remember 3 things, here they are. Keep it simple, abstract things and have clear interfaces to the abstractions, and write a spec. At least write down the abstract state. And one final hint, which is not very actionable, but it's very important. Get it right. If you're doing the wrong thing, it doesn't make any difference whether you followed all these hints or not. And on that note, I'm going to stop.